Okay, Calculus Unit 2, Day 2. I thought maybe we should talk about notation a little bit. It was a little confusing yesterday. When we are talking about the slope of the tangent or the derivative, we used what we call f prime of x. So if you have a function notation would be f at x. We say f at x or f of x, and it means a function using the variable x. And it can be very helpful if we have different functions. We can name them different things like f at x, g at x, h at x, and it can sort out different functions for us. So we were introduced to that in grade 11. If we are finding the slope of the tangent and we are in function notation, we tend to use f prime x to represent the derivative, and we say f prime x or f prime of x. And it refers to the derivative function, the slope of the tangent, when we're in function notation. We're not always in function notation, however, a lot of us are used to seeing our functions as y equals, and we're kind of comfortable with that. So if you have a function that's y equals, our derivative would be dy dx. So we say dy dx, and it refers to the derivative of y. We're just too lazy to say it. The derivative of y with respect to x. That's what it means. And it can be very helpful if you have equations that have more than one variable. So we're going to try and use both of these forms and get you used to it. One thing that I've seen often, and I believe in your textbook as well, is we kind of marry the two and we say y prime. So y prime can also be considered the derivative. I'd like to look at the three examples we did yesterday and just try and generalize them a little bit. We noticed for the function f at x equals x squared, we found that f prime of x, when we did the difference quotient, the limit as h approaches 0, was 2x. Does that make sense if we look at our function? So we're saying the slope of the tangent should look like, or should be represented by, the line 2x. Okay, as best I can, I have drawn f prime x also on the same grid. So let's look at f prime x at 0. So f prime 0 equals 0. You can see that dot on my purple bluish line right there. What that's saying is the slope of the tangent of f at x equals x squared should be 0 right there. And I agree. If we look at our green curve, the slope of the tangent right there is 0. Let's look at another place. As I look at f prime x equals 2x for larger values of x, so let's look at 4. It appears that the slope of the tangent is 8. And that would make sense at that place, that the slope of this green curve would be very straight up there, very steep. And as we go backwards, at x equals -2, it appears the slope of my tangent should be -4. And that seems reasonable. So sometimes looking at a graph of the derivative function can give us a sense of what the tangent slopes are doing on a function. Our second example yesterday was with the function f at x equals square root of x. So I'll draw that as well as I can. Okay, so our square root function. And we said after we found the derivative function by using the limit as h approaches 0 for the difference quotient, we said that it was 1 over 2 root x. I'm going to try and draw that, impose that over top of the same grid. Okay. Okay, so it is a function that has an asymptote here. Oh boy, this is hard on a smartboard. And then it approaches closer and closer up here, nice and tight. Okay. Does that make sense that the slope of the tangent close to 0 would be very, very, very steep and less steep and getting closer and closer to 0 as we travel along, but never actually hit 0 because that function is going to continue to grow. So yes, this derivative function does represent how the slopes of the tangent are changing for different values of x, and we know this is defined for x greater than 0. The last one, let's just look at it quickly, but it's f at x equals 1 over x. And we said that yesterday the derivative function was negative 1 over x squared. Let's see if those make sense. So 1 over x. Really struggling to draw this well. We have 1 over x, our reciprocal function, and then our derivative. Okay, best I can do on this thing would be it approaches 0 and it approaches negative infinity on both sides. Okay. Let's see if this visually makes sense to us. Our blue function, which is our function, has a very steep negative slope here. We can see that our derivative function indicates very negative here. Our slope is closer to negative 1 here. That makes sense. Our tangent function indicates you got a slope of about negative 1 there. And our slope gets less and less steep, getting closer and closer to a slope of 0 as you progress to the right. And you can see our tangent function indicates our slope is getting closer and closer to 0. Looking at the left side, I didn't draw it super well, but we can see that our blue function has a slope that it's getting shallower and shallower in this section over here, and our derivative function is indicating getting closer to 0. We can see our blue function is getting steeper and steeper as we go down over here to the right, and our derivative function, the red one, is showing more and more negative. So sometimes looking at a graph of your function and your derivative function can be helpful. And before we proceed to the cute little rule, I would like to just show you a different form of writing this function. F at x equals x to the negative 1 from our rules of powers is another way to write that. Our derivative function I could write as negative 1 times x to the negative 2. Interesting. Okay, let's go back one slide and we'll look at those two functions and see if you've noticed the rule that we're going to talk about in a minute. I could write my function instead of square root of x, I could write that as x to the 1/2. My derivative function I can write as, so I've got 1 over 2, so I could just write that as 1/2. I've got a square root of x on the bottom, so I could write that as x to the negative, and square root as a power would be 1/2. Look at those two for a second. See if you see the rule. Back to the first one. If my function is x squared, my derivative is 2x. So for those three, we've looked at the graphs, and now we're going to look at the rule. Our power rule for derivatives. For any f at x, that equals a power of x. Our rule for the derivative is, and I hope you saw it, is bring down the power, reduce the exponent by 1. And that's our derivative function. No more limits to get there. You can take this one to the bank. Let's do a few examples. No limits. First one. If f at x equals 7x cubed, then I want to find f prime x, or the derivative in the general case. I'm going to bring my exponent down, so I bring the 3 down. 3 multiplied by 7 is 21, and I reduce my exponent by 1. Done. The second one. I have 3x squared minus 5 root x, and I want the derivative function, f prime x. Since I'm in function notation, I'm going to stick with function notation. So there's 2 separate bits. I'm going to do each one separately. The first one is 3x squared. My power rule is bring down the 2. That now becomes 6. X, and my exponent is reduced by 1. The second part is a little bit trickier. So a good thing that can help you perhaps is to rewrite it as a power. So square root of x is the same as x to the 1/2. So I am going to bring my power down. That makes that 5 halves x to the, and I reduce my power by 1. 1/2 subtract 1 is negative 1/2. So that is my derivative function. It's just not very pretty. And I don't like it when it's not very pretty. So I would rather that you tidy it up. I have 6x subtract 5 over 2. And that x has a negative exponent. So I really should be putting it in the denominator. And 1/2 is really the same thing as root x. And I really think that's prettier. Okay, this one is interesting. I've got f at x equals 3x plus 2. There's a couple of ways to do this one, but one that would certainly be appropriate would be, you know what, I'm not quite sure what to do with that, so I am going to write it out, FOIL it, and then take the derivative, because that always works. So my function, I'm not at the derivative yet, is 9x squared plus 6x plus 6x, which is plus 12x plus 4. And now I can take the derivative. My power rule says bring down the exponent. That becomes 18. Reduce the exponent by 1. Bring down the exponent. This exponent is an invisible 1. So if I bring a 1 down, I still have 12. Reduce the exponent by 1 would be x to the 0. Well, x to the 0 is just the number 1. So I'm not going to write it down. For the last one, I have the number 4, and the number 4 has an implied x to the 0 beside it. If you bring down your exponent, you would have 0 times 4, which is 0. The derivative of any constant is 0. Derivative of a constant is 0. If you want to write down y, you certainly don't have to, but 4 is the same as 4x to the 0. So if you bring the 0 down, you have 0 left over. Okay, last one. F at x equals 1 over x cubed. Another way to write that function would be x to the minus 3. A negative exponent is a flip. So to have something in the denominator, it's easier to use the chain rule if you write it with an exponent in the numerator. So we would end up with our derivative is bring down the exponent, reduce the exponent by 1. Best, prettiest answer would be negative 3 over x to the 4, because a negative exponent would indicate something in the denominator.